So just a quick, I used to be a teacher, so if I wander around, sorry, just out of habit. I'll do my best to kind of stay still. So how many people in here have done causal modeling before? Oh, quite a few. Cool. How many people have never tried it? Should be the opposite, right? Cool. All right, so I'm going to talk a little bit about what we do at Wayfair in terms of causal modeling. The goal for here is, for those of you who are unfamiliar with causal modeling, to come out with at least an understanding of how it's different than predictive modeling. And for those who are familiar with causal modeling, to give you a nice tangible example of how we actually use this in the wild. Cool. So to do that, I'm going to talk about three things. So the first thing, I'm going to give you just a quick background about Wayfair if you're unfamiliar with Wayfair. I think it's really important to understand a little bit about the culture because that actually drives why we are able to do what we're able to do from a data science and a modeling perspective. I'll compare and contrast causal and predictive modeling and why I think those two are a little bit different. And then I'll give you a nice, again, tangible example of what we did and what the results were and how it benefited Wayfair. Cool. All right. So at Wayfair, if you're not familiar, we're the US's largest online furniture retailer. We sell furniture online. Our goal is to help people do this better. A nice kind of way to characterize it is we are an extremely fast-growing company. We have 8 million products in our home. We work 10,000 suppliers, and in last year, we had over $3 billion in revenue. One of the coolest things about Wayfair that's not really on here is well, it sort of is. So it's founder-led. Steve and Neeraj did this a lot, basically bootstrapping, right? So we never really took a lot of money. They did it on their own revenue. And so why I think that's important is because that drives our culture. We are very much a pull your bootstraps up, build it on your own, figure out how to get it done, as opposed to just go out and buy it or borrow from somebody else. And a lot of what we've done is about building and doing things on our own. Cool. So to kind of characterize the business challenge I'm going to talk about today, this is general for everybody. This is the marketing teacher coming out of me. So we have a finite amount of money to spend on advertising. So how do we actually spend those dollars most effectively? If you're in a business, I guarantee you have this problem. And the reason why this is the problem is this quote characterizes it as better than I could ever do. So half of the money I spent on advertising is wasted. The problem is we don't ever know which half, right? Which means you have to spend twice as much money as you really should because you don't really know what's going on. Just to kind of point out, this is from the 1800s. So this is a problem that's plagued business for literally hundreds of years. From Philadelphia, it's the same Wanamaker of the Wanamaker building. Post office, cool. So one of the ways we can actually get more efficient is through different marketing channels. And so the marketing channel that I'm going to talk to you about today is display retargeting. What retargeting is, it's when a customer comes to site, they don't buy anything, and they're off on the internet, and we go out around and try and figure out how to serve them ads. And I'll give you an example of how that actually works if you're unfamiliar with display advertising. The reason why, the reason why I chose display retargeting is, one, it's the channel that I work in, and two, from an efficiency standpoint, one of the nice features about online advertising is we can target at the cookie level. So in theory, if we know the right person who's going to respond to the right advertisement, we can ignore everybody else who's not going to respond, and then you're going to maximize your efficiency, right? So we can eliminate all the wasted dollars. Okay, so if you're not familiar with how retargeting works, this is how a lot of ads are sold online. If it creeps you out afterwards, I'm sorry. It's just how it works. So let's imagine Sally F. She's browsing on Wayfair. She's looking for a kitchen cart, right? She's almost ready to buy. She adds it to her cart, but before she goes ahead and commits to purchasing it, she wants to do a bit of research first, right? So what does Sally do? She goes to her favorite web browser, search engine. In her case, it's Yahoo. Sorry, Google. And she types yahoo.com, right? So as soon as she types yahoo.com, Yahoo says, hey, advertisers, anybody who wants to serve an ad, Sally F is about to load my homepage, and I have 2 pieces of advertising to buy. If you're interested in buying these, you have 50 milliseconds to give me a bid, and I'm going to hold an auction. And after that 50 milliseconds, whoever wins the auction, I'm going to serve their ad, and whoever doesn't, you don't get to serve their ad, right? So the idea is these ads are bought and sold in real-time auctions, and they happen super, super fast, right? To the point where, as a human, even if you ask me to make that decision, I can't do it that fast, right? So as Wayfair, once Yahoo says, hey, this is going to happen, we have to answer 3 questions. So the first one is, do I know Sally F, right? In our case, yeah, right? We saw that cookie on our site just a couple minutes ago. So we can say, yes, I do, right? So then we have to say, do I want to show her an ad? And we're like, Yeah, absolutely. We think she's interested in kitchen carts, so we want to make sure we show her kitchen carts so she's not shopping at somewhere else and she remembers she wants to come back to Wayfair. Once we say, yeah, I do, we have to say, well, how much should I actually pay to show her an ad, right? And all of this is done at, I'm going to light speed's exaggerating, but you get the gist. But it happens so fast that we have to code our decisions into some sort of thoughtful algorithm, right? And this is the key challenge that we have. If we make a bad decision, we put that in the algorithm, it spends a lot of money really fast, and that's really bad. Or it spends no money, and that's also bad, right? So we want to make sure we're building thoughtful algorithms. Okay, so every business wants to do display advertising. You have like a make-buy decision. This is the MBA coming out. So at Wayfair, we said, okay, we could pay somebody to do this on our behalf, or we could figure out how to build the internal ad tech and stack. Like I said, the culture at Wayfair is very much build it on your own. So you can guess what we did. We built this on our own. We built our entire ad tech stack over the last 2 years, so we can build our own algorithms, so we can build our own targeting, and we can serve our own creative. These are all the pieces that go into our Waystack data management platform. There's lots of moving parts in here. Lots of marketing engineering, a little bit of data, well, a lot of data science, I'll not undersell it. And lots of negotiation with external partners. So for today, I am only going to focus on a very, very small chunk of this and how we actually built that part out, because that chunk is incredibly important, right? We have to figure out how we're going to buy and sell ads. All right, so just to give you an example of here is our current, well, one of our bidding algorithms. So our current algorithm we actually write into a decision tree. And like I said, part of the reason is we have to make these decisions at basically light speed. Decision trees you can evaluate really, really fast computationally, so we use that. One of our bidding models has about 625 different bids. So you can imagine from a segmentation standpoint, we have approximately 625 different customer segments that we're willing to pay different amounts for. It accounts for about 1,000 decisions, 2,200 lines of code, and we use like kind of no-brainer or not like reasonable features of recent behavior, right? So what have you done for me lately? And then just general customer demographics, right? So like what do we know about that person that's kind of static? Yeah, cool. All right, so I've used this word effective and efficient, and so I want to make sure I define this because this is what's going to drive why we actually want to use causal modeling. And in our case, effective advertising spend positively influences customer behavior, right? So that's the key point here of if I spend $1 and it doesn't move the needle, that was a wasted dollar, right? If I spend $1 million and only one person who received, like, you know, if I show a TV commercial and spend $1 million in TV commercial and only one person actually responds to that TV commercial, like I spend $1 million to get that single response, right? So we want to make sure that we are effectively spending our advertising dollars, and we measure that by how positively we actually influence customer behavior. Okay, so to do this, you got to build a model. This is where I'm going to compare and contrast predictive and causal modeling. So in the general predictive modeling framework, I'll call this the Causal framework. You're trying to answer this general question, right? Given the state of the world today, what do I expect to happen tomorrow, right? So you observe whatever features, whatever information you have about the world today, and all you want to know is what I observed today, what do I expect tomorrow, right? You're trying to make a best guess. How this contrasts with causal modeling is what you really want to ask in causal modeling is how will the world differ today as a result of X, right? So what we really want to know is why, not if the world is going to be different, but if the world is different, why is it different? That's the piece of causal modeling, right? And so if we think back to effective advertising, we want to make sure that the world is different because we showed an ad. So the business question in a predictive modeling framework is, for this is, to whom should I show ads because they are likely to visit, right? So we go through, we build a predictive model. In our case, who is most likely to come to Wayfair? And then let's show them ads. Seems reasonable. But what we really want to ask is, who is likely to visit because I showed them ads, right? So this is the reverse causality thing, right? So this is the part that I think is the real challenge with display advertising is we can build models that are really good at predicting conversions and predicting click-through and doing all these things. But what we don't want to do is serve someone an ad because they were likely to convert. We want to make sure our ads are causing them to be more likely to convert. That's why we put this into a nice causal framework. Okay, so in a predictive modeling framework, some of your objectives, one of them, you can utilize historical data, right? That's the whole point. You don't have to generate any data. Your goal is you want to maximize the predictive ability, right? So from a very simple OLS framework, you want to maximize R squared, right? In an ideal world, you have an R squared of 1, it's a deterministic system. You know exactly what's going to happen if you can observe all your predictor variables. The other thing about predictive modeling is you really don't care to interpret it, right? That's why we can use deep neural nets and random forests and all of these nice algorithms that are really, really good at making prediction because we don't care about interpreting them. So if we contrast this with causal modeling, 3 things, right? So we can't necessarily use historical data. What we really need in our data is we need random variation. And I'll talk about that, how we generated it, and why historical data doesn't always have that. Our modeling objective is we want to minimize bias. And I'll talk about all the sources of bias that we have in our historical data in a second. And then the last one is we want to maintain interpretability, right? So we want to know if we were to change X by 1 unit, how is the world going to differ tomorrow? Because that's going to inform our decision on what we're going to make about X, right? Sorry, I see people snapping pictures. Okay, cool. So let's frame a research question. It's the academic coming out. In our case, from the business perspective, it's one aspect of our algorithm, one decision criterion we have to make on our algorithm is how many ads should we show to a user on a given day, right? Pretty reasonable. If we had an infinite amount of money, we could show every ad to every user all the time, right? But if you think about it, like let's put your consumer hat on. If I show you an ad once, great, right? Like, okay, now I know about Wayfair and I wasn't really familiar with it. 2, 3, 4 times, all right, not that big a deal. If I start showing you an ad 9, 10, 11, 12 times in a day, you either become ambivalent, right? You just ignore it, or you kind of get angry and you start to react and you react a little bit negatively, right? So we use that mentality to kind of frame how we do, right? So we want to think a little bit about this from the consumer perspective. So in order to actually do the research question, we actually need to reframe this a little bit. So what we want to ask is, at what point does showing one more ad stop increasing the chance a customer will return to Wayfair, right? So if ads scale linearly, then every ad we show should increase some likelihood of returning. But if we just think about this intuitively, we just talked about, if I show you 30 ads in a day, like at some point there's some diminishing marginal return, and probably at some point it like hits the curve, and all of a sudden you're just like, I'm tired of Wayfair, I'm never going back just out of spite. It's like a Seinfeld episode. Cool. Okay, so why can't we use historical data, right? So predictive modeling is a great place to start, but for causal modeling, it's often biased. So in our case, for advertising, we have huge sources of bias, right? So we have customer-driven selection bias. So in this case, browsing online, right? So the amount of time you spend browsing online has to be correlated with the number of ads you're getting, because if you're not online, I can't serve you ads, right? But also, you can think about it, if I'm not online, can I also visit Wayfair? No, right? So those things have to be correlated. Ad blockers, it's a huge self-selection bias, right? There is a certain subset of customer that blocks their ads. That's not a big deal because they've self-selected out of receiving ads, so we don't have to worry about wasting money on them. Another challenge is cross-device browsers, right? So unless you're Facebook or Google and have a phenomenal device graph, like this is a huge challenge. How do we make sure that we're not showing you an impression on one device and not on another device? So another aspect you get in here is you get algorithmic selection bias. And so this is a nature of the RTB. So one of these is misaligned goals, right? So we work with a company called AppNexus. They help us implement our models, but they also have some like brakes on, right? So we can't actually serve as many ads as you want. They add some artificial noise to there. If those goals aren't aligned with what we want to do, that creates some artificial selection bias, right? So like somebody who should have gotten 5 ads didn't because AppNexus made a decision. And we can't necessarily control for that. That kind of goes along with the pacing rules. And then you have buyer-driven selection bias, right? So this is, oh, sorry. So this is Wayfair's driven selection bias, right? So in our historical data, we've had an algorithm, right? And like part of that algorithm is defining clear segments. It's segments that you want to target and segments that you don't want to target, right? So you already can't generalize to the entire population. You can only generalize to the people you've targeted. You also bid on each of those people differently, right? So within those, the likelihood of each of those people getting an ad varies as a function of their customer level characteristics, right? So we've determined the randomness with which they're assigned ads, right? That's not externally determined. So if we're going to do causal modeling, we actually have to solve all of these sources of bias, because if we don't, then our impact of impressions on our response variable, in our case coming back to site, is not going to be correct. And I'll show you an example of how that actually works or why it happens. Cool. Okay, so to eliminate as many sources of bias as possible, we ran a nice randomized field study. Right? So we took a subset of our population and we assigned them to one of 7 treatment groups. Each of the treatment groups, we artificially restricted the number of impressions they could see on a given day. Right? So 6 of the groups you restricted to 1 impression per day, 2 impressions per day, 3 impressions per day, 4, 5, and 6. And then our 7th group, our control, if you think about like traditional experimental design, you would do no ads, right? In our case, we actually didn't want that. That's the wrong control for us. We actually took the cap off. So we showed our 7th group as many ads as possible because you want to know what the upper bound is without like, because there's a chance that if you just go from 0 to 6, you actually do see a linear thing. And if you believe that there's a curve, you have to know what the upper bound is. We ran this for 23 days. We impressed about 150,000 users. One of the nice things about being able to control our own algorithm is it allows us to bid identically across all groups, right? So we can guarantee that every time a user comes up for an auction, we had a 50-50 probability of winning that auction and showing them an ad. So we bid based on inventory characteristics, but completely independent of user characteristics, right? So every piece of inventory, that's a key piece in here, right? So every piece of inventory, every time I could serve you an ad, I had a 50-50 chance of winning that ad, regardless of the piece of inventory and regardless of the user, because we modeled the inventory but ignored the user. And then we actually measured visit frequency during the experiment. What we've shown, and if you look at some of the marketing academic literature, external marketing is really good at getting people back to site. The experience on site is what actually drives conversion. So sorry if you think you drive conversion rate with that. Like, most likely you're probably just getting people back to site. But I could be wrong. One of the challenges of the experiment is, though, while we can guarantee that someone receives no more than a set number of ads, what we can't guarantee is that they receive exactly that number of ads. Right? So we talked about user-driven selection bias, right? Like, if a person is in a group where they should get 5 impressions per day and they're not online, I can't, no matter how hard I try, I can't serve them 5 impressions in a given day. Right? So you still have this bias that comes through. So this is, if you were impressed on a given day, how many impressions did you actually get on a given day? Right? So you can see that we have a nice correlation there. Right? So our treatment worked. And you can tell if we take the cap off, we can really inundate people with ads. Like, you can serve a lot of ads in a hurry. Needless to say, this group was just slightly smaller. One thing to kind of point out, I should have made this more explicit on the graph. Actually, for people who are in the 1 impression per day cap, the average number of impressions they saw when we could show them an impression was actually 1.2. Right? So I said I could artificially restrict the cap, but that's where the algorithmic selection bias, right? So if 2 auctions happen simultaneously on the same ad space, so on Yahoo there was 2 spaces, those auctions happen simultaneously and independently. There is a chance that we could win both of those impressions, and we do win that. It's called an ad collision. So even though we only win 1 impression per day, we still have situations in which you get multiple impressions per day. So we have to correct for that bias. All right, so if you believe we have a good experiment and we control for all these sources of bias, we should be able to run straight OLS and estimate the impact of impressions on visit, right? So you have alpha 0 is your baseline visit rate, so independent of any impressions. We're basically saying impressions at 0, so when you get no impressions, what's the average visit rate? And then how do visits increase as we increase the number of impressions? Make sense? All right, so we ran this thinking we had a good experiment, and you get these results, right? Very simple. Baseline, impact of impressions. So just to remind you, if you forget how to interpret OLS, what that tells me is every impression I show decreases the probability. So to show any impressions is worse than showing no impressions, right? If we were to code this into, just straight up code this into an algorithm, our algorithm would be easy. Bid nothing. Take our entire marketing budget from display retargeting and reallocate it to something else, right? So if you look at this and you don't think about what's really going on and why there's bias, this would lead you to conclude something wrong. But what we know from external studies, right? So we've done true test and control. We can measure tangible lift. So we know there is value in there somewhere. So this can't be right. So we spent a lot of time thinking about, like, well, why? What is the bias we're not accounting for, right? Like, our experiment was great and we had all these things. Well, we have to find the bias and we have to solve it. So again, here's the equation we saw. When we ran this regression, we got funky results. right? So one source of bias we talked about is whether or not a customer is online. We can't observe whether or not a customer is online, right? But what we do know is the amount of time that a customer is online has to influence the number of visits that they make, right? Because they can't make a visit unless they're online. So you at least have some correlation there. We also know that the amount of time that someone's online has to influence the number of impressions they got. So you have some multicollinearity that's going on, right? So does anybody have like a econometrics background? Yeah. Yes. Well, yeah, so we aggregate it over the period. Got it? So it's yeah, but so if you believe visits is a signal of being online, then yeah, you could absolutely do that, and you could flip the regression, you get reasonable results. What we're actually most interested in is the error term over here. So if we could observe everything in the world, right, we would know exactly, we could say conditioning on everything else, right, conditioning on whether or not you're online. What is the independent impact of impressions? So to illustrate that point a little bit more, we can actually decompose, our error term, 0, into two parts, right? So error term, so the part of visits that we can't explain with impression has to be some function of whether or not you're online and a bunch of other unobserved variables. We also know that impressions has to be some function of whether or not you're online. And we also know, because of the previous graph, that it is some function of our treatment condition, right? So what happens is you actually get a confounding variable because the correlation between your error term and your impression is not 0. Right? Just by definition, because we know both of these have to be greater than 0. This is theory driving this, right? We know there's correlation there, which means we have to have bias in our alpha. So how do we fix that? Well, so in econometrics, there is a technique called instrumental variable regression. That's what we use. We found an instrument, and an instrument is a variable that is has two characteristics. So the first one is it's correlated with a predictor, right? In our case, we know frequency cap. We're going to use the treatment group, right? So this is called intention to treat as our instrument. It's used a lot of time in medical. So we're going to use our intention to treat as an instrument, and we know that this has to be correlated with impressions because we can flip back to our graph and you see that nice line, right? There's a positive correlation. So that's great. And we also know it has to be uncorrelated with the emitted variables, right? So a great instrument, the perfect instrument, is also completely uncorrelated with emitted variables. In our case, we randomly assign frequency cap, right? So we know, again, this is theory driving this, that frequency cap has to be uncorrelated with whether or not you're online, right? Whether or not someone's online had nothing to do with what treatment group they got assigned to. Which also means, in this case, frequency cap is also uncorrelated with everything else that we don't observe that drives the number of impressions you get. It has to be. Cool? All right. So once you do that, you actually use what's called a two-stage least squares regression model. And so the first stage is we actually predict our predictor with our instrument. Right? So we use our frequency cap to predict our impressions. And so if you think about this conceptually, what we're doing is we're trying to find what proportion of the variation in impressions that we observe is uncorrelated with everything else. Like that's exactly what we're trying to do, right? So if we make this model or estimate this model and then make a prediction for everybody based on the frequency cap, we know that that amount of variation has to be, because of this, uncorrelated with everything else. So then what we do is, so we estimate this model, we make a prediction for everybody. In our case, we had 6 treatment groups, so you really only have 6 different values of this, right? Like it's kind of silly simple. We use our predicted impressions. Again, this is the proportion of variance in impressions that is uncorrelated with everything else to predict visits. The best part about this is if you have a perfect instrument, I don't have to add any more control variables because I know these are perfectly uncorrelated with anything left in the error term, right? Which also means that our estimates for beta 1 and beta 2 are completely unbiased, and they are the true impact, the true causal impact of impressions on visit. So the reason why I have a quadratic term in here is this is theory driven, right? And we fit multiple models, and this is still the best fitting model. But theory again says, if I say something to you one time, good. If I say something to you 2, 3, 4 times, all right, probably not as good as the first time, but still not bad. If I say something to you too many times, like, you're just going to get angry, right? So we want to make sure we capture that. And I'll tell you the other reason why, because you get some nice properties out of this, right? So when we do this, you'll notice now we have a positive coefficient for impressions, right? So what that means is we do know impressions has some causal impact on whether or not someone's likely to visit, right? The other thing that we can actually do is, because this is quadratic, you can just solve a simple optimization, set it equal to 0, and find what's the maximum number of impressions I should show anybody in a given day to like not go past the curve, right? So if I show you 1 impression per day, it's this much better than none. 2, 3 is actually right here. 3 is right here. The peak is actually up here. We use integer optimization because I can't serve you 2.3 impressions in a given day. I have to serve you 2 or 3. But if we were to serve 4, 5, and 6, like you're starting to kind of lose the impact of impressions, right? That's kind of a cool aspect of this. Got it. So everybody, does that make sense? Again, so the trick is we have the uncorrelated portion of impressions predicting the amount of visits, and you don't have to include anything else. I will caveat this and say your R-squared is extremely tiny. Don't let that freak you out. Because if you really think about conceptually what you're doing is you're trying to explain all of the variance in the consumer decision process, everything that goes on in our head, we're trying to explain all of that by how much one display ad actually changes that. And the fact that it's actually like 0.001. So if you think about that conceptually, like basically we're able to explain 0.1% about the entire decision process, which is actually kind of amazing that a single ad has that much influence. At least it is to me. Like I always think I ignore them, but in our case, we can show people don't. So the other thing you can do is you can quantify like how much lift you get. Again, these visit numbers look really small, but when you put them at the scale of Wayfair's traffic, they are economically meaningful. And to go from no ads to the optimal number of ads, you can get a 26% increase in like your actual visit rate. All right, cool. So to kind of like summarize, again, comparing predictive outcomes and causal outcomes. So in a predictive outcome, we would have concluded that all impressions are bad, and our algorithm would buy nothing, right? We know, like just intuition tells us that's not great. When we do this in the causal framework, we actually conclude that some impressions are good, but not too many, right? Only some. And so we should code our algorithm such that we buy some ads, but not too many. And again, the best part about the model that we estimated, because we estimated a quadratic fit and say that's the best fitting model, is the model will tell you exactly how many to buy. So caveat this is, one detail I forgot to leave in or talk about in an experiment is we did not vary the creative at all. So this is, so really the interpretation of this is for us, showing the exact same message 3 times in a day is the optimal. What we don't know is if we were to vary the message. What we don't know is if we were to vary like the medium, things like that. This is, again, very restrictive, but given how we work, it's a great place to start, and it allows us to make our algorithms a little bit better, right? So how did this business impact? We actually decreased our total ad spend, and we saw no loss in performance, right? So any ad you could tell if we were serving to a customer, on average, more than 3 was wasted money, right? Like you're causing them to do something that they don't really want to do, right? So just by stop serving ads, we save money. So we can take that money and reallocate it to people who we weren't normally serving ads to, maybe reallocate it to a marketing channel, reinvest it in R&D, whatever it may be, right? So by definition, because performance stayed the same and ad spend decreased, we actually increased the efficiency of our dollars, right? So we started to solve the ad waste that we mentioned in the earlier, right? So we know, we are confident that now less than half of our advertising dollars are wasted, like to bring it back to Wanamaker's code. All right, so key takeaways. 1, causal modeling is extremely valuable. When you have a situation in which you want to know why something happens, which, why something happens, which in my experience, business partners actually want to know why. Like if I were to do X, what's going to happen to Y? Like they want to know why. You have to put it in this framework, right? You can't put it in a predictive framework because you can never explain, well, why? Like if your predictions are wrong, why? Well, it could be because somebody made a decision, but the problem is you don't have a counterfactual. Maximizing predictive power without understanding the underlying system does not always lead to good decisions. Again, so if we show the first model, right? So we just maximize, we try to find the best functional form, and we saw that it tells us to not serve any ads. Once we stepped back and thought about like what is the actual underlying system we're trying to model, we realized that there's bias that we didn't account for, and so we need to go through and fix those things to make sure that we're not making bad decisions, but that we're making the right decisions. And then the last part is sometimes you need to be a little bit creative with your randomized experiments just to generate data to model, right? Like we can't just do everything in an A/B experiment. And to be honest, most A/B experiments in the field are heavily ridden with bias, like heavily ridden with bias. So we need to be aware of what that bias is and how do we correct for those things. Cool. So just to tell you, this is more than just like a small snippet. So we actually use some machine learning variations of causal modeling. If you ignore some of the biases, these actually work. So Patrick Story of Hopper, based out of Boston, wrote a nice paper on uplift models, which is basically trying to estimate lift using random forest and cart models. Susan Athey and Guido Imbens, a couple of economists at Stanford, I think Guido used to be at MIT, wrote their version of it, which is basically they took, again, a random forest and a cart model, and they re-specified the objective function to have more economic theory driving principles. And again, like two nice packages that we use to great success, right? It allows us to take some experimental data, subset the people who actually respond, and use that to score customers. Cool. All right, so I'm done. I'm going to do a couple, I want to acknowledge the right people and talk a little bit about data science, and then I'm way open to questions, right? So this is not a single solo project. So Anvesh, Tim, Mike, and Dan are all coworkers of mine. Dan's a manager, and then Mike and Tim's here. So you can talk to Tim afterwards and ask him questions too. And then actually, we worked on this with some academic collaborators. So Sung Ho and Sang Pil are professors at Arizona State. And Ranjit is a professor at University of Missouri, Kansas City. So interestingly, if you paid attention to my bio, it says I'm finishing my PhD. And hopefully about 6 months, you'll be able to read all of this, but the super academic treatment of it, because this is like actually my dissertation. And if you have like holes that you want to poke in it, definitely let me know. I'd rather you guys poke holes than my advisors. Kind of ruthless. But the reason why I want to do that is because what I think this project has turned out so well is because it's been collaboration with people who are in the field and also people who are experts at the econometrics and the theory and the things like that. And so we've been able to blend those two things. And so as you do these things for your own, like, don't ignore academia, and like especially marketing professors. And my bias is like extremely deep in that because I think everything's a consumer choice problem. So there's that. Okay, and then the last thing I want to talk about, I'll describe Wayfair data science in a nutshell. That's like my weak nutshell illustration. This is like super cheesy, but I'll explain why. So I think Wayfair, like when I think of data science at Wayfair, I think it's about diversity, and not necessarily in diversity like traditional diversity. We have that, but where it's really diverse is in two things. So one, the type of projects that we work on. So we're tackling everything from operations type stuff, pricing, on-site personalization recommendations, to marketing attribution, bidding in real time. How do we do all these things, right? So like there's a huge breadth of problems we solve. Hugely diverse, takes a huge amount of skill sets. Which leads to the other part, which is like the most exciting piece of Wayfair diversity to me, is the people that I work with are hugely diverse from schools of thought. So we have people with MBAs, we have people with PhDs in OR and math and engineering and computer science. We have undergrads with degrees in economics and computer science. We have master's students or master's graduates with applied math and all of these things. So what that does is that diversity creates this really rich environment that I can go and ask somebody how to learn whatever it is I need to learn, right? Like if it's like really good software engineer and I need to build something, they're very much willing to help us. And it's these pieces that have allowed like these other things to be really, really successful. Yeah, I think that's it. Cool. Yeah. Questions? Trent. It wasn't a plant, I promise.
Yeah. Why were you optimizing for visits as opposed to revenue?
Because what we've seen, so the question is, why were we optimizing for visits instead of revenue? When we measure the impact of advertising, we do a nice driver-based approach. So if you think of your ad dollars, it can influence multiple parts of the decision process. So one, it can get people back to site. And if you assume that they convert at the same rate and spend the same amount of money every time they convert, just getting people back to site is a win. Two, if people come back to site at the same rate but convert at a higher rate and spend the same amount of money, you're going to make more money that way. And three, if they come back to site at the same rate, convert at the same rate, but buy bigger products, that's how you make more money. So what we found is that if you study where you get lift at all three of those levels, for retargeting, we drive our lift at getting people back to site. Right, so and if you think about it kind of intuitively, like Like you were just on site, and all we're trying to do is just capture that demand, right? That's exactly what we're trying to do. So that's where we get it. That's the question of like, so we go to repeat visits and we trust that that translates to revenue. Yep.
You know about me and deciding how much to bid on me, and you know how much I make, and the ad is about a BMW, would you bid more for having me get that ad?
If I think that ad is going to change your behavior, yes. If I don't think that ad is going to have any impact on your behavior, then no. Like you could be willing to spend $1 million, but if I show you an ad and it doesn't change the probability you're going to spend $1 million, it's a wasted dollar. So for us, it's all about, do we actually change something? It's all about incremental. So that's I don't know if that answers your question. Like we use the demographics because like if we think we can move the needle, like moving the needle on somebody who's likely to buy something more is more valuable than moving the needle on somebody who's likely to buy less. Like that's why we use all the customer characteristics. But the big thing we try and find is like who are most likely to respond to ads. In the back.
So you didn't have experimental data.
Yep.
And all you had was observational data. Do you think this is
Potentially. What you need is some sort of natural experiment or quasi-natural experiment. If you don't have that, then no, you can't use it because you don't have any externally random variation, right? Like if we didn't have experimental data, then I can't know if the variation impressions that I served is just random and that's what's driving it, or if it's some other thing that's driving the random variation in impressions. So for causal modeling, you have to have some sort of, sorry, Dario, exogenous variation. It has to be unrelated to everything else. Yeah.
Did you explore any of the other sort of correlated or uncorrelated variables like location or time, or?
No, because intention to treat works out from an assumption way. It's the perfect, like you can't do any better than that from an instrumental standpoint. It's legitimately like the perfect instrument you can have. Because we randomly assigned it and we know it's uncorrelated with everything else, whereas location or time or anything like that, there's a chance you could argue that it's still correlated with something we unobserve. Does that make sense? So we only ran this experiment on desktop only. So we tried to do that to get rid of all cross-device issues. Everybody, if they were cross-device, we assumed that they would randomly get all the other marketing treatments that they would normally get. We only subsetted this on desktop. So that's like one caveat, right? Like if we could improve this, it would be able to cross-device match people to address that specific problem. But that's a really hard problem. And this is good enough for now. Yeah. So at Wayfair, again, we like to build things. We built our own internal traffic splitting tool. And so for 30 days prior to the experiment, every time anybody came to the site, we would randomly assign them to one of our groups. Once that 30 days hit, our retargeting, so one of the caveats to be in retargeting, like the bare minimum to be a target for retargeting, is you had to be on our site for within the last 30 days. So if we assign people for 30 days and then start the experiment, we know that anybody who would possibly be in retargeting was eligible and they were randomly assigned. So the online bias didn't affect them. What we did was if people came to site, once we started the experiment, we actually excluded all those people. Makes sense?
So what about, I know you mentioned keeping the type of ads was not really good.
Yep.
But have you made any enhancements since holiday season, sweepstakes, or certain type of campaign maybe a more sticky?
So varying the call to action. Have we done any of that stuff? So the data science part of display retargeting has been primarily focused on targeting and bidding. The marketing side is still responsible for creative, so we haven't done any like data science optimization of like what's the best call to action. If we were to change the call to action, as soon as you change your like creative substantially, like those results go out the window, right? Like because if like the response rate to a different creative or different call to action is substantially better, like you don't know that. You have to rerun the experiment. Like that's the kind of downside. The nice thing is like we saved enough money where you could justify spending the extra money to run the experiment again. So it's like you get to like trade off and say like, oh well, the money I saved you, let me play with it. Oh.
It sounds like you care about repeated visitors,
Yep, for specifically for display retargeting, yeah, right? So the goal of that is to take someone who was just on site and get them back to site to convert. So yeah.
Yeah, and how long was the time horizon to assume that the UI didn't change? Like if they go visit the website design stayed the same during your experience?
That's a good question. We didn't, but since people were randomly assigned, their website experience wouldn't be different across treatment groups, so you wouldn't get any difference in response there. Right, like, so it's, if the website changed for like people in the 1 impression per day group compared to the 6 impression per day group, they, yeah, absolutely, that'd be an issue. But because our site splitting tool does everything orthogonally, you don't have to worry about that, right? Like the proportion of people in treatment 6 and treatment 1 who would get the new site design would be the same. That's so. We ran that for like 3 days, and somebody got like a really aggressive 2,000 ads in one day. And so I called my advisors that night. I was like, guys, we can't do uncapped. Like, can we put some reasonable constraint in there? And like, no, we gotta have it uncapped. I was like, somebody got 2,000 ads in a day. And they're like, oh, okay. I was like, and so then you would get through and you could do the data, and like 95% of everybody got less than 40 ads. So we just put a hard cap at 40. And the other argument is like, realistically, like, even though they want to publish this in paper, like, we're never ever going to serve more than 40 ads in a day. Like, one, you have to spend a ton of money, and like, two, that's aggressive. Yeah.
So I thought it was a great presentation.
Thanks.
One thing that I think would be an extra thing worth showing is the verification of your coefficient is sufficient for warranty spending.
Oh, yeah. So I can't share that data for like investor reasons, like it's insider trading because it's fairly recent. But yeah, I mean, like I can assure you that that amount of lift is economically tangible. Like it matters to us. It moves the dollar sign. That's the most I can say. I'm sorry.
So for example, I assume you compare conversion rate and gross profit. You know, you can, I think, present a conceptual equation that gets you there.
Okay.
Interesting to know what elements you consider. Like some companies would do revenue, another would do conversion rate times what you.
Yeah. So to kind of give you like the overview of. Again, we analyzed it at the visit level, the conversion level, and the AOV level. And AOV and conversion were no different, so we held those constant and assumed that if those two are constant across groups and repeat visits go up, then you have to get additional revenue. And so you can say the value of a visit is the same across whether I show you an ad or not, and take that economic value of a visit and apply that to the lift in visits you get, and that's how much money you can say you make. So if we know how much a visit is worth on average, we're driving more of those visits, so by definition, you have to increase money. And we know we didn't decrease conversion rate, and we know we didn't decrease AOV. So it's not like we got people back to site, but got worse people back to site. We got average people back to site. Yeah, right. So what we can do is in the optimization, you can actually go through and we can estimate cost. Where's it at? Whatever, you guys get the idea. Go to the inverted U, and you can also, so that's pure revenue maximizing. You can solve that optimization. You can estimate a cost function because we have data on how much an additional ad costs, and then you can do it in a profit maximizing framework. In that framework, it goes from 3 to 2 ads. And this is more a business decision. We're like, well, we're willing to like risk that 3 ads is not necessarily profit maximizing because we still want to maximize revenue. Does that make sense? Cool. Any other questions? Oh, yeah. No, all the creatives are identical. Yeah, that was one way because to your point earlier, if you have multiple different creatives, like you can't control what point those creatives come in the order, then you get a huge amount of bias that way. So for us, we were interested in only answering the question on average, how many impressions should we show you? And so again, the interpretation of ours is of the same message in a given day, this is the most we should show. There's no notion of if we were to change our message after impression 3, maybe we could add another 3, and then change it again, you could add another 3. Yeah, so our creatives are, basically it's like a white background and there's 6 recommendations. So it's the product you just looked at and then some combination of products that our recommendation engines think you'll like. But they all in general look the same. And they say come back to Wayfair and not we just saw you shopping this, but it's more implied that we just saw you looking at this. Yeah. Yeah, absolutely. So we've done, I just want to do a super simple one, but yeah, you can include customer heterogeneity in a no-LS framework. You just add interaction terms with your impression variable with your instrument, and you could get that and say how it is. Like the other thing you can do is just estimate separate models. Like if you do big blocks of customers of like, do we have your email address or not? Like very easy. Like just estimate a separate model for each of those, and we've done that. So our tree, we didn't just take our entire tree and just add like globally like, oh, don't serve more than 3. We went through and estimated these on an individual level and said like for these subsets of customers, serve 4, for this one serve 2, whatever it may be. Tried to identify what it is for that. Those are additional visits too. Yeah, that's a good question. Sorry, I should have clarified. Yep.
So given your results, what's the next step? I mean, are you going to like refine and perfect this, or are you going to apply it to another outcome in industry?
That's a great question. I think like the academic thing to do would be to go through and like, how do you add a bunch of levels of heterogeneity and like random coefficients, and can you parameterize those things and like tell a really interesting story? For us, like practically, is where you're going to get the biggest like move to the needle, right? So like most likely it's taking this methodology and reapplying it to a different channel and saying like, can we get like a big like, can you chop off a big chunk of inefficient spend so you can reallocate that to somewhere else? Like from a business perspective, it's probably the most straightforward thing to do.
So would running the experiment for longer duration change the beta?
That's a great question. I don't know. There's a chance yes, and there's a chance no. I just don't know what that chance is. But that is like, it's something like for us to definitely look into. Like another thing we didn't account for here is the spacing of ads, right? So like if I show you 3 rapid fire, is that different than if I show you 3 an hour apart? And if you think about that problem, that's actually a really hard problem. And it goes back to, if you're not online, I can't show you an ad, right? So if I want to show you 3 ads and space them an hour apart, and I show you 1 ad now, I may not see you again in an hour. Like, so I don't get that opportunity to do it. So it just adds an extra layer of noise. So the simplest thing is to assume that part away and assume it affects everybody the same. That's an extremely strong assumption, but it's good enough for now. Yep. Cool.
Was the timing of the visits not randomly? Was it just because if that was random, wouldn't it kind of wash out too?
If the timing of if visits were purely random, then you wouldn't see any impact of.
So like you mentioned, like back to back to back.
Yep.
You know, so that ordering, that spacing between, that was random.
It was whatever the market dictated, right? So if like there's certain sites, if you go on, does anybody have a Yahoo email address? Like if you just open it up, if you don't, or find somebody who would do it, it just like cycles ad almost as fast as possible. Or like an Outlook.com email address, literally every time you like click, it's selling another ad. And so those things are actually really easy to buy a ton of ads on. So it's probably more site dependent on that, which is a selection issue because certain customers go to certain types of sites and other customers don't. So our instrument, again, like this is where the instrument comes in and it removes that bias because we know assigning frequency caps to the intention to treat has to be uncorrelated to everything because we assign it randomly. Like that's the nice piece.
So here I'm maybe missing something, but when you did the experiment, you used the number of impressions as your predictor variable.
Yep.
So we do avoid some of the problems you ran into if you just use the cap group that you set them into as your predictor variable.
So yes, but so there's a paper by Angerst and Embens in 1995, and basically you effectively do the same thing, except for if you estimate that model, you have to take the first stage model and you look at the ratio of the coefficients, but that equates to where the ratio of the coefficients is exactly equal to the coefficients of if you use the predicted model as the independent model. So yeah, you're exactly right. It's just not exactly correct. But the ratio of, if we were to use, this to predict this, the ratio of that to that, if you assume that's like delta, gives you exactly that.
Do you have access to the number of opportunities?
We don't. That's like a big downside because you could use that to control for being online, right? Like just like throw that in, you know that that's going to control a lot of your variance and you can get rid of that. I wish. But you also can imagine that if I had the number of ads, opportunities that happen online in any given day, like literally terabytes of data, probably a second. Because lots of people sell lots of ads. Cool.
You mentioned causal trees.
Yep.
Susan Athey, I know she's done a lot of work on that.
Yeah.
Have you, so you've used them to success? I've explored them, but I've never. I'm just curious as to your experience with them. Did you use them for this?
So that's actually the next step for this one, is to take that model and apply it to this data to figure out. So we arbitrarily assign customer segments to get our heterogeneity in there. The next step is to actually use her model to let let that decision process actually define what our customer heterogeneity is. The idea is we can use this now as an unbiased. So the problem with that, with our data, is we know that our impressions are intention to treat as biased because her model takes a pure test and control, and what we were most interested in, the number of impressions. So if we do this and then use our predicted number of impressions as groups, you can start doing, I think you can start doing subgroups, because really we don't have 2 groups to compare, we have like 6 or 7 groups to compare. And that's like, well, I'll have to figure out how to like extend her model to do that, because basically like splits a group, does a t-test, and finds the t-test where the means are the biggest difference, and then says that's the number 1 split. Then goes to the next group, runs a t-test on all possible combinations, whatever the biggest one, it goes there. So it's like super p-value hacking.
And so it's purely looking at one variable.
Yeah, it's yeah. Her models are all built on, and even Patrick's models are all built on you either were in the experiment or not. Ours is, we have multiple different treatment conditions, so that's where it's going to make it a lot harder to do this. We do have a control group, like, because we have a control group for our other measurement that we can actually use as a not treated one. That's kind of where we're going to start exploring and then figuring out how we can introduce this to remove any kind of bias in the treatment. So can we use intention to treat as a nice instrument? And if we don't do that, do we get estimates that make theoretical sense, or do we have a situation in which it just says it drives everybody not to come back to site or not? Like it is the like logical next step, because if you believe in that method, then it should work. The challenge is how do you adapt that method, which is built on just an A/B experiment, to a 7-condition experiment. Susan Athey, or Athey? Athey, sorry. There's a really good paper. I think these slides are going to get shared. I'm going to take the numbers out just for, because I have to. But there's links to Patrick's paper, and there's links to Susan's paper, Susan and Guido's paper in here. The nice thing about these is there's R packages that are already written. So you can just, like for hers, you can just download it on GitHub, and if you make corrections, she'll just pull requests, because I made a couple, so. Cool, anyway.
So one more question.
Yeah.
According to that diagram, so after the 3 visits, after the 3 impressions, the more impressions we have, the fewer visits you get?
Yeah, so you start getting some reaction, right? So from a consumer standpoint, think about it like if you ask someone you sort of know to do you a favor once, probably not that big a deal. But the second time, the third time, like once you ask them the 4th time in the same day, like they're gonna get kind of annoyed with you that you're asking them to do the same thing. Like that's what we're able to see. To kind of dive in theory, there's a psych theory called the mere exposure effect, which is like super common, which is the idea of if you just see something randomly, you're more likely to like it later. And advertising works extremely like that, because we think we ignore advertising, but the fact is you still see it and you process it. The thing with the mere exposure is it actually backfires if you show it too many times, which is what we can validate in this.
I think it also the person who got 4 ads, at one point they only see 1 ad. If they went after that, if they visited after that 1 ad, then they were really 1 ad group anyway. Well, they weren't. I mean, I know you randomly assign them, so yeah, you explain everything to that, but you can.
Yeah, so that's potential confound in terms of we didn't look by day and say you saw 1 ad even though you're in the 4 ad group and came back after the 1st ad. We looked at this at the aggregate level, and the ability to, the instrument allows us to get rid of that, because we still are looking at the completely independent variation in impressions and how that affects visits overall.
So visits is a discrete variable, not continuous.
It's count.
Right, so I'm curious why you didn't use a mean distribution.
So I did. It's just easier to explain OLS. So we have enough data to where like your basically the coefficients are going to be, they're going to show the same sign, but you're going to get we get better model fit with a zero inflated negative binomial, because you have huge zero inflation. That's your best fitting model, but I didn't want that to be the point of what we're doing. Like it's way easier to explain in OLS and like know the estimates still work the same. Yeah, you have to, because we wouldn't. I mean, we don't have any information on it, And this is where random assignment helps us, is because people were randomly assigned, you'd have to assume, even if they're not random, they're random across, like within, or sorry, between our groups. So that that randomness helps us out. Cool. Oh.
What was your collaboration like with AppNexus on this? Did you?
So AppNexus is the platform we use to actually implement our bidding model. So what they do is their technology allows us to write our own trees, which is a huge thing, right? Like we wouldn't be able to do this if we didn't write our own trees. And they give us access to all the seats, right? So that's basically what we did with them. The rest of it is we turned everything we could that AppNexus implicitly does for everybody to kind of help them out. We try to turn all of that stuff off because it's some sort of bias, or it's a source of bias that we can't control and can't explain. So we wanted to get rid of all that. Like I've cleared out the room. All right, thank you guys.